Here are solutions to homework set number 6 for ECE 461-661 control systems. Now this homework looks at mass spring systems, rotational systems, and DC motors. The first problem is, given this mass spring system, find the transfer function from force to x2. Now the way we do it is convert this to a circuit equivalent and then write the node equations, write the state space equations, throw it into MATLAB, solve. So the first step is to write the circuit equivalent. What I do is I've got 3 degrees of freedom, x1, x2, x3, so I have 3 voltages, x1, x2, x3. Each voltage has inertia, draw that to ground, inertia to ground, inertia to ground, then start filling them in. The first mass has a spring to mass 2, a spring of 4 to mass 2, and that's it. The second mass has a spring to mass 3, a spring to mass 3. It has friction to ground. It has a spring to ground and a force. That's a current source. 50-50 shot on the direction. What this says is if the current is positive, it raises the voltage. If the force is positive, it increases the displacement. That's consistent, so I got the sign right. Then mass 3, already did that. So there's your circuit equivalent. Now write your voltage node equations. And that would be at node 1, all the admittances attached to the node, 0.2s squared plus 3 plus 4 times x1, minus the admittances between nodes 1 and 2, 3 and 4, times x2, is the current to the node. At node 2, everybody attached to it, 3 plus 4 plus 3s squared plus 0.1s plus 2 plus 6 plus 5, x2, minus the admittances between 2 and 1, times x1, minus the admittances between 2 and 3, times x3, is the current to the node. Then at node 3, everybody attached to it, times x3, minus the admittances between nodes 2 and 3, times x2, is 0. So there's your dynamics. On the test, this is about as far as you'll go on the test. On the homework, I can now solve. The trick is solve for the highest derivative. So in doing some algebra, solving for the highest derivative, I get these 3 equations. I can now put that in state space form. So my states are going to be position, velocity. Their derivative gives you this matrix. So here's the zeros matrix. Here's the identity matrix. The derivative of position is velocity. That's what this shows, zeros, identity. These dynamics appear in the last 3 rows. So the second derivative of x1 is minus 35x1 plus 35x2. And what I like doing is, just as a reminder, the first column is times x1, times x2, times x3, times sx1, sx2, and sx3. So that's your minus 35, 35. The second equation, minus 0.033 sx2, minus 6.67 x2, plus 2.33 x1, plus 3.667 x3, plus 0.333 f. And likewise, third equation. That's now state space form. So there's my A matrix, there's my B matrix. My C matrix is what I'm measuring. I am measuring, what am I measuring? x2. So my C matrix will pull off the second state. So input the A matrix, and I just did it as the zeros matrix, identity matrix. Call that K, your spring matrix, your friction matrix. Put it all together, A. However you want to do it, it's your pick. Get that into MATLAB. And just as a check the eigenvalues. This is a passive system, so it should be stable. And it is, so there's your poles, that's the eigenvalues. Input the B matrix. The C matrix, I'm pulling up the second state, that's x2. D is 0. Throw it in MATLAB in state space form. Now find the transfer function, and voila! That's the transfer function from force to x2. I can plot the step response in MATLAB. Let's go to 20 seconds. Y is the step response plotted, and that's what I get. That's not unexpected. Again, here's the poles. This one's your dominant pole, should be oscillating at 0.73 radians per second. And here the period from here to here is, what is that? 4 to 12, 8 seconds. So the omega is 2 pi over 8. 6/8 is about 0.7. So yep, that's your dominant pole. Problem 2. Repeat for a second mass spring system. And again, the trick is I've got 3 degrees of freedom, x1, x2, x3. I have 3 voltage nodes, x1, x2, x3. Each node has inertia to ground. So do this guy first. Just as a reminder, inertia is always relative to ground. That's Einstein's theory of relativity. If you don't do that, you're violating Einstein's theory of relativity. It's got to go to ground. Or another way to think about it, if mass 2 and mass 3 don't exist, mass 1 still has inertia. It's always relative to ground, not the other masses. Once I do that, start filling them in. I've got 15 Newton meters between mass 1 and ground. Right here. 0.5 newtons per meter per second. Between 1 and 2, 10. Between 1 and 2, 0.4 s. Between 2 and 3, 5. Between 2 and 3, 0.3 s. And then a force on mass 3. So there's your circuit equivalent. Now write the node equations. At the first node, everybody attached to it, which is all these guys, times x1, minus the admittances between nodes. Between 1 and 2 is 0.4 s and 10. At node 2, take all the admittances attached to node 2, which is all these puppies. Oops. Not sure what just happened there. All these puppies times x2, minus the admittances between 2 and 1 times x1, minus the admittances between 2 and 3 times x3 is the current of the node, and likewise at node 3. To put this in state space form, I'll solve for the highest derivative. Then same as before. If my states are position, velocity, I get the derivative of position, velocity, that's your zeros matrix, identity matrix. These dynamics show up in the third and fourth, 5, and 6 rows. So the first one is minus 0.9 sx, right here, minus 25 x1, plus 0.4 sx2, plus 10 x2 is 0, and so on. Throw that into MATLAB. Here's your A matrix. There's your B matrix. There's A, there's B. By C matrix, I want to know the transfer function to x3, the third state. So I pull off the third state with C, input that into MATLAB, find the transfer function, and here you are. And note that the poles are the same as the eigenvalues. So this tells me the settling time ought to be about 40 seconds. 4 over 0.1, and it should oscillate at 2.38 radians per second. If I plot the step response, it settles out in about 40 seconds, and the dominant pole, let's see, that's 1, 2, 3, 4, 5, 6. 6 cycles in 16 seconds times 2 pi. That gives you something. So 6 over 16 times 2 times pi. That's your 2.36 radians per second. That's that frequency. That is right here. Should be 2.38 radians per second. Problem 3. For rotational systems, very similar approach. I've got 3 inertias. So I have 3 masses to ground, or 3 nodes. Theta 1, theta 2, theta 3, called Q because theta is not on my word processor. Each node has inertia to ground. Then fill in everything else. I've got a torque on theta 1. I've got a spring. That spring goes to friction and a gear, a 1:5 turn ratio. On the other side of the gear, I've got inertia to ground. I've got a spring that goes to another gear. And I've got friction. Then I got another gear. Gear goes to inertia and spring. So there's your circuit equivalent. To get rid of the gears, I'll bring everything left. So everything in this part is going to be times where I'm going to divided by where I'm coming from squared. Everything over here is times where I'm going to divided by where I'm coming from, which is 5 times 5, 25 squared. So when I do that, I'll redraw the circuit. These are divided by 25. These are divided by 25 squared. Now, write your node equations. So here's theta 1, theta 2 star. It's slightly different than theta 2. There's a turn ratio in there. Theta 3 star. Write your node equations, same as before. All the admittances attached to the node times theta 1 minus the admittances between nodes times theta 2 is the current of the node. Likewise at node 2, likewise at node 3, gives you 3 equations, 3 unknowns. Solve for the highest derivative. Plug in numbers. I get these equations. Put in state space form, same as we did before. Here's your A matrix. There's your B matrix. So throw that into MATLAB. Here's your A matrix, B matrix. I'm going to look at theta 1 as my output. Just for fun, here's the eigenvalues. Find the transfer function, and here you are. So it says, here's my dominant pole. That should behave like a first-order system. Plot the step response. It looks like a first-order system, no oscillations. Settling time is about 40 seconds. About. Problem 4, given a motor, find the dynamics. I know from the lecture notes that speed is related to voltage by this transfer function. I need 5 parameters, and I'm not given those parameters. So inertia is not given, correction. Inductance is not given, so let's assume 0. The torque constant I can find, that's this guy right here, is 14 volts per kilo RPM. I've got to convert that to volts per rating per second. So converting kilovolt, kilo RPM, 1,000 revolutions. 1 kilo revolution is 1,000 revolutions. Let's see, 1 minute is 60 seconds, and 1 revolution is 2 pi radians. Gives you, these cancel, this cancels, this cancels. Gives you volts seconds per radian, or volts per radian per second. So there's kT. D, you kind of have to back into. The node load current is 0.5 amps. There is current coming in, so there's power being dissipated. That has to be the friction. So 3404 RPM is 356 radians per second. Power is volts times amps, which is torque times speed. I've got 48 volts drawing 0.5 amps. That's the power coming in. That must be the power going out. So friction amounts to 0.0673 Newton meters. That's your friction constant times speed. Again, speed is right here. Tells me my friction constant should be about 188.9 times 10 to the minus 6 Newton meters per radian per second. Inertia. Again, this is not given, so you got to do some back of the envelope calculations, best wild ass guess. I know the diameter of the motor is 50 millimeters. That's got the case. So let's assume the shaft, assume this is 10 centimeters, or 10 millimeters, 10 millimeters. Let's assume the shaft is 30 millimeters, solid iron, that's 89 millimeters long. Again, wrong, probably, but I don't really have a lot else to go by. And in that case, I can find the mass, or the volume. The volume is 63 cc's. If it's iron, iron has a density of 7.87 grams per cc. It's 496 grams, about a pound. The rotational inertia of a solid cylinder is 1/2 mr squared. So throwing it in, assuming a solid iron shaft, 30 millimeters diameter, 89 millimeters long, here's J. And again, that's probably wrong, but kind of give a wild-ass guess based upon what I know. So with that, if L is 0, here's the dynamics in general. Throw out L, this becomes the dynamics. I know J, D, KT, R, L. So this is the denominator polynomial. It's JR times S. So this is the S term. Here's the 1 term in the denominator. The numerator is just KT. So here's my transfer function for the motor. If I add a weight to it, like have this motor drive a bicycle at 20 miles per hour, I know what kind of gear reduction I need. 20 miles per hour is 8.9 meters per second. The motor is spinning at 319 radians per second, and for a gear, or a wheel, the velocity is r times rotational speed. So there's the velocity, there's the rotational speed, find the radius. I need a radius of 28 millimeters. The inertia of the bike relative to that. So here I've got my displacement x, here's theta. I have x is r times theta. So this inertia right here, which is 100 kilograms, goes through the gear as the turn ratio squared. So multiplied by r squared, this is the inertia relative to the motor. So take the previous inertia, add 0.078 kilogram meter squared to it. That's the net inertia, the bicycle plus the motor. And with that, I wind up with this transfer function. And kind of note, this is really, really large. The inertia I calculated was 10 to the minus 6. Basically doesn't matter. So I don't really know what the inertia of the motor is. In this case, I don't really care. The 100 kilograms is going to be really dominating it. If I take the step response, it takes about 4 over 0.34, 11 seconds to get up to speed, which seems reasonable. You floor the bicycle, 11 seconds later, you're 20 miles an hour. And the voltage I need. The DC gain is 7.3, so 1 volt in gives you 7 radians per second. To have it go 319 radians per second, I need 43 volts. So that's homework set number 6 for 461.